Recording finely sampled data with large number of sensors is costly, tedious, and may not be feasible always. So in this video, I am going to talk about how to efficiently reconstruct full near surface wave field from fewer sampled traces. In this video, I will mainly discuss about two things. First, the problems related to the conventional near surface data acquisition design, and then the compressive sensing based reconstruction of full wave field record from fewer sampled traces. The surface wave method is a widely used seismic technique for non-intrusive investigation of Earth's subsurface. Among different surface wave methods, the multi-channel analysis of surface waves or MSW technique is extensively used to produce multimodal dispersion images from the recorded wave field. Traditionally, dense and regularly spaced sensor array is used to acquire surface wave data. There, the array is designed according to sampling theorem, which states that the wavelength must be greater than or equal to twice of the sensor spacing, which will otherwise cause spatial aliasing. However, sometimes obstacles or physically inaccessible areas like buildings or roads make the regular sensor deployment infeasible, creating large gaps in the acquired data. Also, the high cost of these sensors may limit the receiver spread length while following the regular spatial sampling design. The effect of these missing traces on the data processing and interpretation is huge. For the conventional regularly sampled dense short gather, we can see a clear spectrum in the frequency wave number domain. However, when there are large gaps in the acquired short gather, the artifacts are clearly visible in the frequency wave number spectrum. The spatial aliases heavily masks the original FK spectrum that will hamper the further data processing. Compressive sensing based sampling theory is a new paradigm that suggests that we can recover a full wave field from fewer sampled traces depending on some criteria, among which the three key ones are an efficient sampling scheme in the measurement domain, which sufficiently characterizes the sparse transform domain like the Fourier or Redon domain wave field components, and lastly, a suitable optimization algorithm for recovering the full wave field from the observed data. The concept of efficient sampling can be elaborated using a simple time series of combined sinusoids. When we perform traditional theory-based regular sampling, we can clearly see the three sine waves in the frequency spectrum. However, when we uniformly subsample the time series violating the sampling criteria, we can incur heavy aliasing in the frequency spectrum, which makes the identification of the original signal difficult. Instead, if we perform random subsampling, it will convert the aliased energy to low amplitude background noise, allowing us to discern the original spectrum easily. The compressive sensing based method can recover the data fairly well. Here we can see that we have achieved an efficient reconstruction of the missing traces, and the FK spectrum is also free of aliased energy. The reconstructed wave field and its Fourier spectrum highly resembles the original dense array data and its FK spectrum. The low difference between the original and the reconstructed short gather clearly depicts the effectivity of compressive sensing based sampling and reconstruction technique. That's all for this video. Thanks for listening, and if you like this video, please subscribe to our YouTube channel for more videos like this.